Hey, Chloe. Glad you could join me today. I've been looking into this fascinating research on hybrid levitation microactuators and their static pull-in behavior. It's quite a deep dive into how tiny devices can levitate without touching anything.
Hi, Liam. Yeah, that sounds really intriguing. Micro-actuators that levitate? Like no physical contact at all? That's wild. How do they even manage that?
Exactly. So these devices use electromagnetic levitation to hold or move microscopic objects without any mechanical attachment. At such small scales, friction is a huge problem. It tends to dominate and mess up performance. So contactless suspension is a real game changer.
Right? Friction at the microscale can be a nightmare. So these hybrid levitation microactuators, HLMA, right? They combine magnetic and electrostatic forces to keep things stable?
Yes, that's the idea. They use a mix of magnetic fields and electrostatic forces to levitate and precisely control tiny objects, like microdisks. This hybrid approach offers more control and stability than using just one force type.
Interesting, but I imagine keeping something levitated without touching it is tricky. What's this static pull-in behavior they're studying?
Good question. Pull-in instability happens when the electrostatic forces pull the levitated object too close to an electrode, causing it to snap in suddenly and lose stable levitation. Think of it like a magnet snapping onto a fridge when it gets too close.
Ah, I see. So in classic electrostatic actuators, pull-in is pretty well understood. But with these hybrid devices, the magnetic forces add complexity.
Exactly. The magnetic suspension creates a nonlinear spring effect. The magnetic forces don't just change linearly with position. That makes predicting when pull-in happens much harder.
That sounds complicated. And I guess modeling these systems isn't straightforward either?
Not at all. The electromagnetic fields are governed by Maxwell's equations, which are notoriously complex. Solving them for microscale devices with complicated shapes is a huge challenge. Even commercial simulation software struggles to capture all aspects, especially stability and nonlinear dynamics.
So what's the solution? How do the researchers tackle this modeling problem?
They developed a clever approach combining a quasi-finite element method, quasi-FEM, with analytical modeling. Instead of solving the full field equations, they divide the levitated microobject into many small circular loops, or filaments. Each loop represents a tiny circuit where eddy currents flow.
Eddy currents. That's like those swirling currents induced inside a conductor when exposed to changing magnetic fields, right? Like little whirlpools of electricity?
Exactly. So, by calculating the mutual inductance, the magnetic coupling between these loops and the coils generating the magnetic field, the model predicts the distribution of eddy currents inside the levitated disk.
That's smart. So instead of wrestling with complicated field equations, they reduce the problem to solving a set of linear equations for these currents?
Yes, and that's a big deal because it avoids the need to solve nonlinear differential equations, which are much harder and slower to compute.
And the analytical model simplifies things even further?
Right. It approximates the eddy currents as just one or two main circular circuits. Think of it like approximating a complex whirlpool by just two main swirling currents to understand its behavior. This makes calculations faster and more practical for design purposes.
That analogy really helps. So they have this detailed quasi-FEM for accuracy and an analytical model for speed and convenience.
Exactly. Now, to test these models, they built an experimental prototype, a tiny disk about 2.8 millimeters in diameter, levitated by two coaxial microcoils on a substrate.
Two coils? How do they work together?
The coils carry alternating current at 10 megahertz, creating magnetic fields that induce eddy currents in the disk. These eddy currents generate forces that levitate the disk. Then, electrodes placed near the disk apply electrostatic forces to perform pull-in actuation.
And they measure the disk's movement with a laser sensor?
Yes, a laser distance sensor with micrometer precision tracks the disk's displacement as voltage is applied to the electrodes. This setup lets them see exactly when pull-in happens.
So what did the simulations show about the eddy currents in the disk?
The simulations revealed that in the center of the disk, the eddy currents flow opposite to the coil current negative sign, while near the edges, the currents are positive. The strongest eddy currents concentrate along the disk's edge and along a circle matching the levitation coil's diameter.
That's fascinating. So this pattern justifies the analytical model's approximation of two main eddy current circuits?
Exactly. The two main circuits correspond to these areas of maximum eddy current. The forces on these circuits differ. One mainly lifts the disk vertically, while the other pushes it horizontally.
For the pull-in actuation they studied, the horizontal force is small enough to ignore?
Yes, which simplifies the model to focus on the vertical force interaction between the levitation coil and the main eddy current circuit.
So the pull-in model balances gravity, magnetic levitation force, and electrostatic attraction?
Precisely, and the models predict pull-in displacement and voltage with good accuracy. Errors range from about 5 to 30%, depending on disk size and conditions.
That's pretty good, considering the complexity. I imagine the quasi-FEM is more accurate but takes longer to compute?
Yes, the quasi-FEM is computationally heavier, but more precise. The analytical model is simpler and faster, making it useful for practical design and quick estimates.
Did they test disks of different sizes?
They did. Disks of 2.4, 2.8, and 3.2 millimeters in diameter were tested. The experimental data matched well with both models, validating the approach.
That's reassuring. So the models can predict how changing disk size or levitation height affects pull-in behavior.
Exactly, which is crucial for designing reliable devices. Knowing these parameters helps engineers avoid unstable operation.
Why is understanding pull-in behavior so important in these microactuators?
Because pull-in instability can cause the device to fail or lose control. For applications like microsensors, micromotors, or microaccelerometers, stable operation is essential.
And this modeling approach helps engineers design devices more efficiently, avoiding costly trial and error?
Yes, that's a big advantage. The combination of simulation and analytical models offers both accuracy and speed, a powerful tool for microactuator development.
Plus, these contactless devices help overcome friction and wear issues at small scales, right?
Exactly. That means longer-lasting micromachines and more sensitive sensors. It opens doors to new technologies in robotics and precision instrumentation.
So to wrap up, this research shows how clever modeling can predict complex behaviors in tiny levitating devices without solving complicated nonlinear equations.
Yes, it's a great example of blending physics, engineering, and smart approximations to make these microactuators practical and reliable.
It's amazing how much goes into making something so small work so precisely.
Absolutely. And this work really pushes the boundaries of microscale technology.
Thanks for walking me through this, Liam. It's been a fascinating journey.
My pleasure, Chloe. Always great to explore these cutting-edge topics together.